Swayam Prabha. Digital India. Educated India.
Welcome to NMR spectroscopy, carbon-13, carbon-12 combined. We're going to look at three isomers of C7H14O. So that's just the molecular formula. You can have different structures, and using these spectra, you're going to find the exact structure of the isomer. So here's your chance to hit that pause button, work it out on your own, and then turn on the video. Let's look at it. Let's do one at a time and see, how we can solve them. First of all, we talked a little bit about 13 carbon before. Just a brief review about carbon-13. Carbon-13 is a carbon NMR that will tell you the different environments a carbon can be found. So if you have a carbon 0 to about 50, it's typically in an alkyl range. Tertiary would be higher than secondary, secondary would be higher than primary. If you had something about, up to about 90, those could be alkyl protons that are next to electronegative atoms like halogens, nitrogens, oxygens. Now this region between like 100 to 180 are typically vinylic protons, so typically double bonds. Benzenes would appear in that region. Above that, 160 to about 220 would be C double bond O carbons, carbonyl carbons. Again, these are only showing you the carbon. So here there are three different types of carbons. Even though you have 7 in the formula, there are only 3 different environments. Therefore, you would expect a lot more symmetry there in that molecule. Here you have 1, 2, 3, 4, 5 different environments. So little less symmetry than there. Even then, you don't have 7 different environments, so there is some symmetry in the molecule. All of the spectra were run in CDCl3, so you will see 77, you would have a peak, and you can calibrate the machine using that. Now, if you have 3 peaks and 7 carbons, obviously, you would have a lot more symmetry here. Now, what about this? Why is this like drawn out of the scale? That's because it's literally off scale. So the machine draws from 0 to 200. It says offset 40, going to 240, but there's no room to draw it, so it puts it in just like your carboxylic acid on your NMR. There was an offset. So here this could be 200 plus an additional 20, about 220. If it's 220, then we know that it's very, very, very de-shielded, the most de-shielded carbons, and those are typically carbonyls. So all of these are going to have a carbonyl. What type of carbonyl? Is it going to be an aldehyde or a ketone? It cannot be carboxylic acids, esters, and so on, because there's only one oxygen. So it could be an aldehyde or a ketone. If you had an aldehyde, you would see somewhere here between, above 9, a proton for this molecule. So therefore, you don't have any aldehydes because there are no peaks here above 9. So all of these are isomeric ketones. That's what you can say from your spectra. So let's see what are the possibilities for these. Now, it would help, since you have a large molecular formula, to keep in mind that there is symmetry. So you have a CO and R groups here. If these R groups are identical and you have symmetry, the number of peaks would decrease or become half if they're exactly the same. So keeping that in mind, you could say if this is your carbonyl CO, what is your alkyl chain going to look like? All right, let's figure that out using our proton NMR. Here are 3 peaks. Let's do the same thing, A, B, C. So you have 3 peaks here, one around 0.9 delta. You have a triplet, a very nice triplet. At around 1.7, you have a beautiful 1, 2, 3, 4, 5, 6, a sextet. And we've seen those before. And over at C, which is at 2.4, you see a beautiful triplet again. Now, in terms of de-shielding here, you know that C is the most de-shielded. Therefore, it's probably the one closest to the carbonyl. These are going away from the carbonyl. Let's look at some more pieces of information. How many protons do we see below each one of these? For that, we have to grab our ruler. Look at the height ratio here. This is about 2, this is about 2, and this is about 3. So that's a 2 to 3 ratio. 3, and this is 2, 2. That's only going to be 7, but we have 14. What does that tell you? That means they're identical, they're symmetric. So therefore, this is the ratio. So this is going to be 6 to 4 to 4 because you have 2 sides to this molecule. Let's look at the neighbors. Those are really important. This A is a triplet, which means n plus 1 is 3. Triplet is 3. That means you have 2 neighbors. This is a sextet, n plus 1 is 6, so you have 5 neighbors. You're in a really crowded neighborhood there. Time to get out. N plus 1 is 3, triplet is a 3, therefore n is going to be 2. So if you take this ratio on one side, you cannot put 6 hydrogens on 1 carbon, obviously. So these are 2 CH3s. These are 2 CH2s, and these are 2 CH2s. So we have 2 CH2s and 2 CH2s and 2 CH3s. That's what it means. All right. So let's look at the possibilities. How can we put CH2, CH2, CH3? Well, let's put it just like it sounds. 3 carbons in a row. Well, that kind of corroborates that those are your alkyl carbons. And let's see, you need to have 2 triplets. That means 2 of these carbons should have a neighbor that has 2 hydrogens. So these are going to split this however many hydrogens into a triplet, and these will split these however many, 1, 2 or 3, doesn't really matter. It would split this into a triplet. So this is going to be split by this 2 plus 1, 3 triplet, and same here, 2 plus 1, 3 triplet. Let's look at who's on the triplet. So you have somebody who has 3 hydrogens and somebody who has 2 hydrogens. Let's put them in. So here, this is going to be a triplet because of the neighboring 2 hydrogens, and this is going to be a triplet because of these 2 hydrogens. All right, so here's a typical triplet, sextet, triplet. That was one of our trends, and we see that here. Well, that's only 3 carbons. What about the rest of the 4? Well, we know it's symmetric because we only have 3 peaks, so this is repeated on the other side. And what's tying them together? There should be something in between. Well, what about this guy? So let's draw that over here. CH2, CH2, CH3 always gives you a triplet, sextet, triplet, and that was one of our trends. We have here C6H14. So we only have a carbon and an oxygen left. Obviously, we cannot put the oxygen here because then you would have a delta for this close to 4, and we have nothing like that. We have 2.4, and that's around 2 is typically what your delta would be if you are a neighbor of a carbonyl. So this is going to be your d-shielded 2.4 delta ppm hydrogens, this and this. Therefore, you have 4 of them. These two are going to be the next most d-shielded, because now these are 2 carbons away. And so therefore, that's going to be your 1.7 ppm. And these are typically in the alkyl, and it's primary, and so it's about, close to 0.9 ppm. In terms of the carbon 13 proton, who do you think this guy is? Well, it's about 45. 45 is typically in the neighborhood of a carbonyl. So if I label this A, B, and C, again, this is going to be the most d-shielded, and through inductive effect, it's going to fall off with distance. So this is going to be A, B, and C. And we know primary is going to also have the lowest delta for carbon 13. And since this is exactly symmetric along this line, the machine cannot tell the difference between this and this. So these are going to be identical, which is why you have 3 peaks instead of 6 here. Carbonyl, carbon is always going to be very, very d-shielded here. And if I say D here, that is going to be your D carbon. In terms of hydrogens, well, we already talked about it. This is the most d-shielded triplet. So these are your HCs. These are your next most d-shielded HB. And you would expect 2 plus 3, 5 hydrogens, 5 plus 1, 6. That's why you are seeing a sextet here. And you would see the exact same pattern over here. So here's one isomer. Let's look at the others. Let's see how we can find all 3. All right. Let's go over here. We have 2 peaks here, and there's one little teeny peak over here. Okay. And we know it's hard to even see that, but we know that's from the carbonyl. Sometimes you can't even see them. They're almost like noise on the baseline. So over here, let's look at these and look at the ratio. This is 20 and this is 40. So 40 is probably the one that's closest to the carbonyl. These are away. Well, why do I say carbonyl? Well, look at the formula, because they all have these peaks here. Well, we should have started with our delta here, but it's never too late. Delta 7 times 2 plus 2 is going to be 16 minus 14 divided by 2. Oxygen, you don't add or subtract anything. That's going to be a 1. So we know that there's one unsaturation, and since we're seeing a peak in the carbonyl region, that's going to be a ketone. So let's look at the structure of this particular ketone here. A, B here. A is going to be a very big doublet, and B is going to be 1, 2, 3, 4, 5, 6, 7 septet. All right. So this is going to be at 1.0, and this is at 2.9. So here's your septet multiplicity, and this is your delta ppm and doublet. And let's look at the number of hydrogens hidden beneath that proton. All right, so let's look at the height ratio here. This is about 1.5, and this is 9. So let's write that down. Number of hydrogens. This is going to be 9 centimeters. This is 1.5. Divide both sides by 1.5. That is going to be 6 to 1. Oh, we've seen 6 to 1 and doublet septet. What do you think that is? That's right. Let's write it out here. So we know we have a carbonyl, and in addition we have a doublet and a septet. In order to have septet, you need to have 6 hydrogens that are identical. The only way to get that is to have 2 methyl groups that are identical. So here is your 6 hydrogens, and that's going to be a neighbor to this, which is going to have just 1 hydrogen. So over here you will have 1 hydrogen. So this hydrogen is going to split all 6 into a doublet. And all these 6 hydrogens are going to split this 6 plus 1, 7 into a septet. Well, that only is 3 carbons. What about the rest? And there's 1 carbonyl. Do we have more carbons here? Let's look at it. There's only 2 types of environments, and here they're almost like a 1 to 2 ratio, but then we never look at integration or ratio here for C13 NMR. They're not reliable. Therefore, we only know that we have 2 types of carbons here. This is 1 type and this is 1 type. And here, that's in a very de-shielded environment, we have 1. And we know this is when you have about 220, it's typically ketones and aldehydes. So therefore, this is going to be symmetric. So that means you have 2 of these and held together by a carbonyl. So does that make sense in terms of a delta value of the NMR? If you have a carbonyl here, this is going to be very, very de-shielded, and it would be close to about 2.8. So the exact structure for this would be totally symmetric, with this reflected onto this side, and so you have a very symmetric molecule. So let's draw that out. So on this side also you have the exact same things, CH3, CH3. So let's label this B and label this A. And does that make sense in terms of splitting? What would we expect for a B? A B, this is septet, so 6 plus 1 is 7 septet. Therefore, N is going to be 6. So it does have 6 neighbors. Over here, this is all being split into a doublet. So N plus 1 is 2. Therefore, N is going to be 1. It only has 1 neighbor. So it's perfect. If I label this B and A, B is going to be more de-shielded. So this is going to be B and this is going to be your carbon A. And all of these are carbon A's. This is going to be your most de-shielded carbonyl carbon. All right, so we got 2 figured out. Let's do this one, C. Let's look at number 3. We have another ketone. We have 3 singlets, but we have 4 peaks in the C13 NMR, as I said, actually 5 with this, as I said. The number of peaks here don't always correspond to this. So let's look at all of the possibilities here. Let's first write them down, A, B, and C. And so here we have A is going to be a singlet, A, B, C. The ppm for both of these are going to be, for all 3, about 1.0 in the alkyl region mainly. And so this is about 2.2. And let's look at the multiplicity. Pretty much nothing. We just have singlet, singlet, singlet. That means none of these guys have any neighbors. They want to be all on their own on some mountain top doing their own thing. They don't want to be bothered by other hydrogens next door. How do we have 3 singlets in for this formula when you have so many hydrogens? So we have to find the hydrogen ratio to see how these all 3 of these can be singlets. Let's look at it. This is 1, 1.5, and this is about 4.5. 1, 1.5, and 4.5. Well, if you add these all up, this is about 7. We need 14. Well, we know they all have to be doubled. Times 2, 3 times 2, that's 9. So it's a 2 to 3 to 9 ratio here. And yes, they add up to 14. So we're fine with that. Let's look at the number of neighboring hydrogens that are processing on either side. All singlets, so therefore you have no neighbors. N is 0. Same here. So 9 hydrogens, 3 hydrogens, and 2. How can you get 9 hydrogens all identical without neighbors? There's only one possibility, and we saw that we have either 3 hydrogens singlet or 9 hydrogens singlet. We can have 2 possibilities, CH3X, where X has no hydrogens, or Y has no hydrogens, that's a singlet. CH3, 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 and over here you could put whatever you want. It doesn't have to be something that doesn't have hydrogens, because this is the neighboring carbon and there's no hydrogens here. So these are typically where you have a 3 hydrogen singlet and a 9 hydrogen singlet. Okay, so we know this is probably due to a T-butyl group. So let's draw out our tertiary butyl group. So let's put these pieces together. We have a tertiary butyl. That's the only way you can get 9 hydrogens as a singlet. What else do we have? All the way here, this is about 220. We know that is a carbonyl, and we also know we have an oxygen, and if it's that de-shielded, it's definitely going to be a carbonyl. So this is another piece of the puzzle. So we have then a CH2 and a CH3 that we have to figure out where to put. Where would you think you can put those? If it is a CH2, well, it's got to have 2 arms holding somebody on either side. And in this case, since our oxygen is already occupied with the carbonyl, it's just got to be 2 carbons on either side. So we have a choice of putting a CH2 here or here. But CH2 is inside the molecule. CH3 is the cap. So if you were to draw a CH3, it's better to put it here than here, and because we cannot connect that. So here is your CH3, and therefore the CH2 is the one that's going here in the middle. Let's check it out. Let's see if this is the correct structure. So here is our carbonyl, and since we've been doing carbonyl, this is the carbonyl peak for 13 carbon around 220 ppm. So we know we have a carbonyl carbon. These are probably going to be the ones that have the tall peak, because you have 3 of these. And over here too, you have 9 hydrogens. So these are your C protons here, and this is going to be your hydrogen C. Does it make sense? Yes, 9 hydrogens, no neighboring hydrogen here, 3 bonds away. So this is going to be N plus 1 is 1, N is 0, so you get a singlet with 9 hydrogens. Over here, this is going to have no neighboring hydrogens here. There's a carbonyl and a quaternary carbon. So therefore, this is also going to be a singlet. Over here, this has a neighbor that is a carbonyl. So this is also going to be a singlet. N plus 1 is going to be 1 for singlet. N is 0, no neighbors. This is your singlet. This is going to be your 3 hydrogens singlet. So these are your HBs. And this is your CB. And this is your A protons. And we can say this is your A carbon. And these would be very, very similar in their delta values. So these could be your Ca, Cb, and of course this is going to be your carbonyl around 220 ppm. So that gives us 3 different isomers, all with different spectra, and it makes it a lot easier to figure out your compounds when you have both your NMR and your C13. Thank you guys for your attention, and please don't hesitate to ask me if you have any questions. Practice, 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 and I will see you soon with some combination problems. Talk to you later. Bye.